So welcome to Big Ideas, Algebra 2, Section 4.3, Part 2, which would be polynomial synthetic division. In the Part 1 of this section, we did polynomial long division, which is useful for dividing any polynomials, but it can get a little tedious, and synthetic division is a method that's going to be a little bit faster and more convenient. However, you can only use synthetic division when your divisor, that means whatever you're dividing by, is a linear factor with a leading coefficient of 1. What this means is when you are dividing a polynomial, if you are dividing that polynomial by x minus 3, then that's a linear factor because it's x to the first power, and the leading coefficient is 1, so that's fine. But you couldn't use it if you were dividing by x squared minus 3 because it's not linear, so that one doesn't work. And you also cannot use it if you're dividing by 2x minus 3 because it's a linear factor, but it's not a leading coefficient of 1, so that's why that one doesn't work either. We actually can do this case here. It's not suggested in Algebra 2, but at the end of this video, I'm going to show you how you can actually use synthetic division when you're trying to divide out a linear term that has a leading coefficient other than 1. So we're going to do the same problem as what we did in part 1 of the lesson, which was the long division. We're going to take 2x squared minus x minus 3, and we're going to divide that by x plus 1. The way we're going to set it up, though, looks different than long division. I'm going to start by taking the coefficients from the dividend, so that would be 2, negative 1, and negative 3. So I'm going to just write those out, 2, negative 1, and negative 3. And then I'm going to look at what I'm dividing by. I'm dividing by x plus 1. So if x plus 1 is the factor, we're going to actually set that equal to 0 and solve for what the root of that would be. If x plus 1 equals 0, then that means that x would equal negative 1. So I actually am going to set up a synthetic division bracket, and I'm going to be putting a negative 1 on the outside of that bracket. You may have seen this as synthetic substitution from earlier in the chapter. So I'm going to go ahead and follow that synthetic substitution process or synthetic division process, and which is just a series of multiplying and adding. Here's how that works. I'm going to drop the 2 down, and then I'm going to multiply negative 1, which is over here on the outside, times 2. Negative 1 times 2 is negative 2, which I'm going to stick over here. And then I'm going to add negative 1 plus negative 2 to get negative 3. Then I'm going to just repeat that process. So I'm going to take negative 1 times negative 3, which is positive 3. I'll put that up in the next spot. And then I'm going to add those, and I get negative 3 plus 3 is 0. So then, that's my answer, but it's not written in the correct form. In order to get this in the correct form, I need to think about the degree of my dividend and the fact that I was dividing by a linear expression. So because the degree of the dividend was 2, but I was dividing it by an x to the first power, that means that my leading term in the quotient would also be linear because I'm going to subtract these exponents. So if 2 minus 1 is 1, then that means that this would be 2x to the first power minus 3 for the constant term. And the last number that comes over here, that's the remainder. So if you want, you can put a box always for that last term so that you can remind yourself that that last number is going to be the remainder. But you don't have to. You can just remember that that's the remainder. So it turns out then that this answer would be 2x minus 3 with a remainder of 0. Hope that makes sense. Let's do a couple more examples. In this next example, which is also one that we did with long division, in part 1 of this lesson. The interesting thing, or the reason why this was an item of note, was that there was no quadratic term in the dividend. And so we had to put in a 0 placeholder when we did long division. The same is true for synthetic division. So I'm going to take the coefficients. That would be 1x cubed. 0x squared is what's going to have to stick right there. So 0x squared, negative 4x, and 12. If I'm dividing it by x plus 3, and I think about what number then that would produce over on the left, if I set x plus 3 equal to 0, the factor of x plus 3 produces a root of x would equal negative 3. So I'm going to put negative 3 on the outside, and then I'm going to follow my synthetic division steps. So the 1 is going to drop down. Then I multiply. Negative 3 times 1 is negative 3, and I add. Then I multiply. Negative 3 times negative 3 is 9, and then I add. Then I multiply. Negative 3 times 5 is negative 15, and then I add. And now I just have to write out the answer. So let's look at the original problem. I started with a cubic, but I was dividing by a linear, and so if I look at those exponents, 3 minus 1 is 2, so I know that my answer exponent has to begin with a quadratic term. There, it's a quadratic exponent, which means this answer would be 1x squared minus 3x plus 5, and then this last number here, that's the remainder, so then that would be plus negative 3 over x plus 3. As you can see, this is a faster way of dividing than long division, but the tricky part is that because it's synthetic division, we're just playing around with the numbers, we're playing around with the coefficients, and so you don't really see what you're doing in order to divide. And so then you have to be extra careful that when you get your answer that you understand how to interpret the numbers 1, negative 3, 5, negative 3 to actually write the answer correctly there. But there you go, that's synthetic division. So we have a story problem and then some other things that we can do with synthetic division. Here's the story problem we're going to look at. It says the polynomial x cubed plus 7x squared minus 38x minus 240 expresses the volume in cubic inches of a box. One of the dimensions is x plus 5 units. What are the box's dimensions? So I know that volume of a box is going to be length times width times height. And so I know that I need 3 factors. And if I know one of them, if I divide that out, then maybe I can find what the other 2 are using another method. So I'm going to use synthetic division and take my coefficients, 1, 7, negative 38, and negative 240. And I'm going to divide out this factor of x plus 5. It says that that is one dimension, which means that hopefully that means it should divide cleanly. So if x plus 5 equals 0, then negative 5 is the number that would go on the outside there. And I'll complete the synthetic division. So drop the 1 down, and then multiply, and add, multiply, and add, multiply, and add. And I did get a remainder of 0, which is always nice, because that means that that divided cleanly. And what I have left, if I started with a cubic, what I have left would be a quadratic. So this would be x squared plus 2x minus 48. The summary statement for this division problem that I just did would say that if I took x cubed plus 7x squared minus 38x minus 240, and I divide that by x plus 5, this is the answer that I got, that equals the x squared plus 2x minus 48. I can also rewrite that as a multiplication problem to say that the original volume of a box, the x cubed plus 7x squared minus 38 x minus 240, that equals x plus 5 times x squared plus 2x minus 48. That's helpful to see it as a multiplication problem because now I can see that I have it written, the volume written as two distinct factors, the x plus 5 factor and then the x squared plus 2x minus 48 factor. Well, I need three factors because the problem is asking me for the box's dimensions and I don't have any other hints, but I can divide this quadratic. So this is actually, sorry, I meant factor, this quadratic. So this is actually x plus 5 times, and then let's just factor this. I know that this would be x and 6 and 8, and we'd have to have a positive 8 and a negative 6. So it turns out that this expression for the volume of the box, I'll go ahead and set that equal to V for volume, equals x plus 5 times x minus 6 times x plus 8. That's as far as we can actually go with this. We can't say what numerical dimensions the box has because we were never told what x was. But I could, for instance, make up that if x was 10, let's say, then if the x was 10, then the length would be 10 plus 5, which is 15. The width would be 10 minus 6, which is 4. And the height would be 10 plus 8, which is 18. It doesn't really matter which one of those is which. Because you could simply turn the box on its side or flip it upside down, spin it around, and so we're not given any restrictions on which dimension is which. This would just be an example if x happens to equal 10, right? You could let x equal 11 or 12 or anything greater than 6 actually, and this would still make sense. All right, another application that we would have of synthetic division is the remainder theorem. So the remainder theorem is like synthetic substitution from 4.1. In fact, it is synthetic substitution from 4.1. If I want to evaluate a function, the old way, which would be the direct way that you were taught in Algebra 1, would be to say that P of 3 is 3 to the 5th minus 8 times 3 cubed minus 3 squared plus 2. And then to know that 3 to the 5th would be 243 minus 8 times 27. So let's see, 8 times 30 would be 240. And then subtract 24, so 216. And then minus 3 squared, so minus 9, and then plus 2. And then to say that 243 minus 216 would be 27 minus 9 plus 2, so 18 plus 2, which is 20. P of 3 equals 20. With a calculator, that's not so bad. Without a calculator, that's a little bit of a pain. The synthetic division way is that we can synthetically substitute that value. So I'm going to write 1x to the 5th, 0x to the 4th, negative 8x cubed, negative 1x squared, 0x, and 2. And I want to substitute the value of 3, so I'm going to put a 3 out here. 3 is the x value, the x equals 3, so it's not negative 3 like we were doing before. It's not the opposite sign because I'm given the 0, not the factor, so I'm okay with that. Like I'm given the number that I'm applying for x. And so now let's just synthetically follow this up and see what we get. Drop down the 1. 1 times 3 is 3. Add, and multiply and add, and multiply and add, and multiply and add, and multiply and add, and I get 20 for the remainder. The remainder theorem says that synthetically dividing a polynomial gives us the function's value at a, which is f of a. So notice I got the same thing, but this was way less work with way smaller numbers, and I also got that p of 3 would equal 20. Technically, this should be that we're dividing it by x minus a. Sorry about that. So that's the remainder theorem. There's a corollary of that called the factor theorem that says that if the remainder is 0, that means that it divided cleanly, which means that the x minus a is a factor of your polynomial, which is going to be helpful for us later in the chapter. So that's the lesson. That's 4.3 part 2. If you are interested in the bonus knowledge of how can we actually divide when we have a leading coefficient other than 1, the answer is that you can and you can't. So this is another example that we did yesterday in the first part of the lesson. If I take 6x squared minus 5x minus 7, and I want to set up to divide by the factor of 2x plus 1, well, if I solve 2x plus 1 equals 0 to see the value of x, the value of x would equal negative 1/2. So logically, you might think that you could just put a negative 1/2 here and do the problem the same way. Turns out that that's not actually true. That's actually taking and dividing out x plus 1/2, not 2x plus 1. The 2x plus 1, the 2 part of it, is not being accounted for because that would still be remaining out there. So if I put the negative 1/2 on the outside, I'm not actually going to be dividing by a factor of 2. Let's try it and see what we get. If we drop down the 6 and we multiply by negative 1/2, then that would be negative 3. Negative 5 and negative 3 make negative 8. And let's multiply by negative 1/2, which would be a positive 4. And then add, and I have negative 3. So this looks like it would be 6x minus 8, and then a remainder of negative 3. But that's only halfway right. So only partly right. The 6 and the negative 8 have not been divided by the 2 yet, and so I need to actually divide them by the 2. The negative 3 is the remainder, so it hasn't been divided by anything yet, which means that I'm going to take the 6 and the negative 8 and divide them in half and get a 3 and a negative 4, and so the answer would be 3x minus 4 and then plus negative 3 over 2x plus 1. This is the main reason that we don't show this in Algebra 2 most of the time, is that students can really get quite confused here because we're going to have to divide part of the numbers by this coefficient, but not the remainder because the remainder hasn't been divided by anything anyways, and we've got a fractional number on the outside of the synthetic division bar, which can cause problems and confusion. But there you go, there you have it. In case you want to try that on your own, feel free to do that. So there's 4.3 part 2.